Hello everyone, I am Rahman Kahtani. Today I will talk about the project that I have been working on with my colleagues Abdullah and Abadi. Now to begin with the chapter 17, wireless signals and modulation. Well, you have to know that RF signal generation and alternating current in an antenna creates moving electric and magnetic fields that propagate as traveling waves. Now, it has key characteristics. The frequency unit is hertz, cycles per second, and the RF range is 3 kilohertz to 300 gigahertz. We have also the wavelength unit lambda, which is basically the physical distance of one cycle. And you have to know that when the lambda decreases, the frequency increases. Now we have also free space path loss, FSPL, which is basically the weakening of signal strength due to wave spreading. Now the FSPL is greater at higher frequencies. So as a result of that, 2.4 gigahertz devices have a greater effective range than 5-6 gigahertz devices. Now about wireless power measurement, we have the absolute power, which measured in watts or milliwatts, and we have the decibel, dB, a logarithmic comparison of one power measurement to another, and we have dBm, absolute power, compared to a 1 milliwatt reference, and we have dBi, antenna gain, compared to an ideal isotropic antenna, and we have EIRP, effective isotropic radiated power, which is the actual power radiated from the antenna. And the EIRP formula is the power plus the antenna gain minus the cable loss, minus connector loss. Now they are in the formula here, they are measured in dBm, dBi, dB, but they can be added directly because they are all the same logarithmic scale. But also there is another way to calculate it. You can convert the power from dBm to milliwatt. How? You just take 10 to the power of the power in dBm over 10. And you convert the antenna gain from dBi to linear gain, which is basically 10 to the power antenna gain over 10. And you convert the cable loss from dB to linear loss factor, which is also 10 to the power the loss over 10. And the same thing for the connector loss. Then it will be, you will calculate EIRP in milliwatt, which is the power in milliwatt times the linear gain over a linear loss factor. And then you'll convert the EIRP back to the dBm, which is 10 log 10 of EIRP in milliwatt. Now, power measurement dB, dBm, dBi. dB is the relative comparison of power. dBm, absolute signal power relative to 1 milliwatt. dBi, antenna gain relative to isotropic antenna. And when the power is double, the dB increased by 3. When it's divided by 2, it's the dB decreased by 3, minus 3. When it's multiplied by 10, it will be the dB plus 10 dB. When it's divided by 10, it will be minus 10 dB. And lastly, about chapter 17, we have signal quality and modulation. About the signal quality, we have RSSI, received signal strength indicator, the measure of signal's power level. And we have also the noise floor, the average signal strength of the noise. And then we calculate the SNR, signal to noise ratio, which is the difference between RSSI and noise floor. And we have the modulation, which is altering a characteristic of the carrier signal, frequency, phase, or amplitude to encode data bits. And we have spread spectrum techniques, DSSS, direct sequence spread spectrum, which is used in 2.4 gigahertz band. And we have dBm, off DM, which is orthogonal frequency division multiplexing, uses multiple subcarriers, and it leverages QAM, quadrature amplitude modulation, to modulate phase and amplitude. And we have dynamic rate shifting, DRS, where devices negotiate the best modulation data rate based on the current SNR, signal-to-noise ratio, where less complex modulation means lower data rate but greater range. And now with my colleague Abdullah Qalaula part, chapter 8.
Assalamu alaikum wa rahmatullahi wa barakatuh. As my friend has finished his part about chapter 17 in our course project for COE446, which is about mobile computing wireless networks. He finished just the RF signals physics and propagations, and now I'll talk about my part, which is the wireless deployment modules. So basically, we have three models in the wireless deployment models: the autonomous system, which is the access points, the centralized one, and the controllerless. The autonomous system, the access point type is autonomous, nothing know about each other. It is self-contained and it's standalone. The centralized is a lightweight AP, connect the wireless LAN control via the tunnels, which is the CAP/WAP client traffic LANs, to the WLC. Then we have the controller list, which is the embedded WC, a regular access point that runs the WC software embedded within it. So runs the WC software embedded inside the AP. Now we have the lab operating modules. We have the local, the flex, connect, monitor, and bridge. These are the modes. The local, which offers the base stations, server clients, scans other channels for noise or other devices. Then we have the Flex Connect, which is the access point at a remote site, maintains the control tunnel, but switches data traffic locally only. Useful if the one links fails. What about the monitor? It is a dedicated sensor that checks for IDS, which is the intrusion detection system, events, and detects rogue and access points. So it helps the intrusion detection systems. Then we have the bridge, which is used for dedicated point-to-point or mesh. Okay, what is the APWC pairing processes? We have the access point boots, which is the access points power ons. Then they have the WC discovery when the AP finds candidates control using methods. And also we have a DHCP option 43, which is specific for this one. We have the CAP/WAP tunnel. AP builds a secure data TLS. What the difference between TLS and data TLS? TLS for TCP and the data TLS or DTLS is for UDP. Then the WC join and config. AP selects the WC and downloads the required image. After that, the run state, the AP is functional and accept the clients. The configuration segmentation, we have the site tag, the RF tag, and the policy tag. The site tag, which is the AP profile and the flex profile. Then we have the RF tag, which is the RF profile. Then we have the policy tag, which is the WLAN profile and policy profile. Example functions, as you can see here. Then we have the configurations segmentation. We have discussed these also. Now we have the antennas and coverage. We have three types of antennas: the omnidirectional, the directional, and parabolic dish. The omnidirectional is donut shaped. The directional is focusing energy in general direction. It is like a beam, and the parabolic dish, which is highly focused, narrowed elliptical beam. The antennas are passive devices that provide gain by shaping RF. Then we have the radiation pattern, which shows the signal strength around the antenna. How the antenna shows the signal. Then the polarization, which are the transmitters and the receiver polarization, must match to prevent severe signal degradation. Means that every transmitter and receiver polarization must have the same signals. In summary, we covered the electrical logarithmic dBm ERP, and I think my friend has discussed how the EIRP is calculated, and the modulation by the OFDM, which is the and the QAM framework of wireless signals. And in chapter 18, we have covered the architectural models, which are the centralized and the flex connect in coverage. Then we have the key takeaways that mastery of these concepts is foundational for designing, implementing, and troubleshooting the robust wireless networks. So really, these two chapters is two of the most important chapters in CCIE and CCNP, because it's explained too much about wireless things. And thank you so much. You can ask us about whatever you want on LinkedIn, me and my friend Abdul Rahman. Thank you so